So now we're starting a new unit, a new chapter even, based on something called a vector. And for those of you who are taking or have taken physics, this will actually seem fairly familiar to you. First, we want to define what a vector actually is. And our definition is that it is a directed line segment, and it's going to have both a length and a direction. So you can kind of summarize this by thinking of an arrow that is pointing. It's going to have a starting point and an ending point. The vector is the arrow that's going along that path. So by saying directed, I just mean that the arrow is indicating which direction we're going along it. It's not going backwards. It's going from the bottom left to the top right in this case. It does have a length, so if I had a ruler handy, I could pull it out and measure how long this line is, and I would get some kind of a length, like 2.5 inches. And the direction can be indicated by some sort of an angle. I know that there is an angle indicated in here that's telling me exactly where that line is pointing. So those components combine together to form what we call a vector. Notation-wise, we note vectors by using this sort of sharper pointed parentheses. So the regular parentheses is still used to indicate a coordinate. So the point AB, for example, if you do this sharper parentheses, that's what's going to indicate the vector, which is starting from the origin in this case and ending at that coordinate. So we already know that if you have a point like 2, 3, we'll pretend that's what we're dealing with in this case, then you're going right 2 units and up 3 units, and you're drawing a dot. That's what the coordinate 2, 3 does. Now that we're talking about the vector 2, 3, that's where our line comes in that's going right 2 units and up 3 units to end at that location. And so what's really marking the difference here is that this is an arrow that lands at the point 2, 3 instead of just a dot at the location 2, 3. So that's the idea of a vector compared to a coordinate, and make sure you understand the notation. We'll be looking for those sharp pointed parentheses on there. When you see the sharp pointed parentheses, we call that component form of a vector. So whenever you see a question ask you for a component form, they're asking you to describe the motion of the vector. How far did it move left or right for the first part, and how far did it move up or down for the second part? The magnitude of a vector is what we use to denote its length, and that's what I have listed up here. The length, or magnitude, is another term that we usually use for it. And you'll notice it's essentially the distance formula. So if you have 2 coordinates, you can do the second coordinate, the x2, y2 value, and subtract the first coordinate, x1, y1. You're going to square both those values and then take the square root of that whole answer. So the magnitude will tell us how long the arrow is, whether it's 2 inches or 30 inches or whatever the case may be. The other terms that you may see come up are things like the terminal point or the initial point. So the initial point is just defining where the graph is starting, and the terminal point is defining where the vector is ending. So we have our starting and ending points. This one rule that is frequently used dealing with vectors is called the head minus tail rule. It's essentially the same as what we were just talking about with the component form. So if we have a starting position and an ending position for 2 different coordinates, then we can find what the vector is by doing the x coordinates subtracted and the y coordinates subtracted. So in this case, if you did 3 minus 0, comma, 4 minus 0, and then simplified this, that would be telling me that the component form of this vector is 3, 4. So now I know that this line here is going right 3 units and up 4 units. Now what's interesting about vectors is that the starting and ending locations don't really matter to us so much as what the vector is doing to the coordinates. So this vector over here is actually essentially the same because it's going from -1 minus -4, so +4, comma, 6 minus 2. Since this vector describes the exact same motion, it's going right 3 and up 4, we consider these equivalent vectors. So they're starting at different positions, ending at different positions, but since their motion is the same, we consider them the same vector. So do keep that in mind. Sometimes questions may ask you if the vectors are equivalent. Just use your head minus tail rule or your ending point minus your starting point to find the component form and compare those vectors to see if they're equivalent or not. So many of your starting examples are just going to give you 2 coordinates on a graph, and if it helps you, you are certainly welcome to sketch those out. I think it's a good idea while you're starting with this section. So we have one coordinate starting at -3, 4, which means going left 3 and up 4, we'll draw a dot. And then the other coordinate is going to go left 5, up 2. So in this case, we have a point, -3, up 4, and then -5, up 2. They want us to find the length going from point P to point Q. So starting from this one up here and ending down here at this one. Now notice it's not always going to be going to the right. You have to be careful about the order they've indicated with their notation here. This is saying starting from P and ending at Q because the arrow is pointing towards Q. So start from this point, go this way, and then that means for our vector, we need to be doing the ending point. So -5 minus -3 and 2 minus 4. And that means this vector is going left 2 and down 2. And that agrees with what I kind of see here on the graph as well. Now again, it's completely possible to do this without sketching the points and drawing the line in there. Later on, you will have to do some of the sketches more for the answers, but I think it'll help you here in the beginning just to understand what we're showing. We're showing that the vector is going left 2 units and down 2 units, which I can see in my graph. Now that's the component form that they asked us for. They also asked us to find the magnitude of the graph. So for the magnitude, let's look back at what I gave you guys for the formula on this. We said the magnitude is, notation looks like absolute value of v, because absolute value is actually defined as the distance from the origin. So in this case, we're just saying what's the distance from one coordinate to the next coordinate. So I can set up the magnitude is equal to the square root of x2 minus x1 plus y2 minus y1. And then when we compute these values, we're going to have -2 squared plus -2 squared. And you'll notice if you already did the component form, your values should be the same here, because in both cases we're evaluating x2 minus x1 and y2 minus y1. That's the same information we're plugging in down here. And then when I evaluate -2 squared, we get 4 plus 4. And make sure you always simplify your radicals instead of just leaving it as square root of 8. If you want to make a factor tree to break this down, you can. The idea is that you're looking for 2 numbers that multiply together to give you 8, and then 2 numbers that multiply together to give you 2, and then we're looking for 2 of a kind since this is a square root. So that lets me bring 1 2 out, and it leaves the other 2 at the bottom of the branches inside of the radical. So this is equal to 2 root 2. So that's just the technique for how to simplify radicals. Make sure you always break those down just like you should always simplify a fraction. So it's not a very pretty value, but what we've found is that the length from our starting point to our ending point, if we measured that distance, it would be a length of 2 root 2. Now this is actually an interesting one because the sides were the same. We could have broken this down into a 45, 45, 90 triangle. And then if the sides were length 2, which is what we have for both the horizontal and the vertical motion, a 45, 45, 90 triangle, you can find the hypotenuse by doing the side times root 2. That's why you may have already known what this value is going to end up equaling, 2 root 2, based on sides of length 2 for a triangle. Okay, one more quick example. Again, let's find the component form. And so for our component form, we're going to have x2 minus x1. And then for the y coordinates, y2 minus y1, which means I have a vector going right 5 units and up 2 units. And for our magnitude, now I showed you guys that the x2 minus x1 squared, that's the same value that we just did here. So if you want to save yourself time, you can just take those numbers you listed and write it's going to be the difference in the x's squared plus the difference in the y's squared. If you want to write out the whole thing, you can. I'm just pointing out that you've already computed x2 minus x1 and y2 minus y1. So it will be faster if you can just jump to this point. And then we can finish this by computing 5 squared is 25 and 2 squared is 4. And the square root of 29 cannot actually be broken down. If you try to make a factor tray out of that, we don't have numbers that multiply together to equal 29. So there's no way to simplify this radical. We just have to leave it that way. If you wanted to sketch the graph, you can, of course. You would draw the two coordinates, and then we have our starting point P, our ending point Q. So it would be an arrow starting from here, going towards the other coordinate. And what we've found is that essentially you're going right 5 units and up 2 units to go from the first point to the second point. And we found that the length is square root of 29, which should be a little bit bigger than 5, so like 5.4, somewhere around there. So we know how long the vector is, and we know what motion the vector is making. And that's all for the notes. Thank you.